In this video, I want to talk about the non-inverting amplifier circuit. So up until now, the circuits that we have used and analyzed, they were inverting amplifier circuits. So we had this negative sign in the equation that basically meant whatever the voltage at input is, the output will be multiplied by a gain and a negative sign. So now let's take a look at a circuit that is an example of a non-inverting amplifier. So here is the circuit that we have here. So this is the op-amp. We have again RF connected between the output and the inverting input of the amplifier, the op-amp, and that is what gives us the negative feedback that is necessary for us to be able to extend the linear region and avoid going through the saturations with small changes in the input voltage. We have RS to be connected this time between the inverting input and the ground. And as for the input voltage, now we have VG, which is connected to the non-inverting input of the op-amp using a resistor. Here I call it RS. So you see here we have RS here, we have RS here, right? So these two are the same. So now how can we analyze this circuit? So the first thing that we do is we write down the constraint that we have. We have Vn equals Vp and then In equals Ip equals 0. So we have In here, we have Ip here, and then Vn and Vp are labeled like this. They are considered as voltage rises from a common or reference node, which is these three lines, and conceptually it looks as if they are connected all with a wire. So now based on this equation, what we can do, as we did before, we can write down the KCL for this node and see what we get. So if I write down the KCL for this node, considering all the currents to be leaving, we have Vn over Rs. This is this current. We have Vn minus Vo over Rf. And then the last one is In, that we don't have any equations for it, so I just simply put it as In. So we know from the second constraint that this equals 0. And we know from the first constraint that Vn equals Vp, right? But unlike the previous circuit, since Vp is not directly connected to ground, we cannot say Vn is also 0, right? So now based on this, let's just write down the equation that shows the relationship between Vn and Vo. So we have 1 over Rs plus 1 over Rf multiplied by Vn equals 1 over Rf Vo, right? So this is the direct relationship from this one, if I rearrange it. So now I can easily write Vo to be 1 plus Rf over Rs multiplied by Vn. So what I did here is that I multiplied both sides with Rf. So if I do that, that is the equation that I have. So now we have the relationship between Vo and Vn, but still we don't know what is the relationship between Vn and VG here, which is our input voltage, right? So from the first constraint, we know that Vn equals Vp. So based on this, we know that Vo equals 1 plus Rf over Rs multiplied by Vp now, right? But now, what is the relationship between Vp and Vg? So to answer this question, let's just take a look at this part of the circuit. We have Vg connected between this node and the common node. We have Rs in series with Vg. And then after Rs, we have the positive side of the Vp and the negative side, which is also connected to the reference node. So now if I want to write down the equation practically in this loop, right, assuming that these make a loop from negative side of Vg through Rs and then from positive to negative side of Vp. I want to get the value for Vp. So we have negative Vg plus Rs Ip plus Vp equals 0. But what happens is that from the second constraint that we have here, this one is the first one. From the second constraint, we know that Ip equals 0. So when Ip equals 0, from the second constraint, we realize that Vp equals Vg. So for Ip being 0, basically whatever voltage that we apply here for Vg is going to be present at the non-inverting terminal of the op-amp. So now based on these final conclusions, we can easily write Vo as 1 plus Rf over Rs multiplied by Vg. And as you can see now, since both Rf and Rs are positive values, so the ratio is also positive. And then we have 1 plus a positive value, so this gain is now positive. So whatever is the sign of Vg, we will have a voltage with the same sign as Vo. So that is why this is called the non-inverting amplifier circuit. So there is another way to come up with this conclusion. It's practically the same method, right? But interpreted differently. So for this approach, our assumption is still preserved. So we have Ip here, we have In here, we have Vp equals Vn, we have Ip equals In equals 0. So based on Ip being 0, we know that Vg equals Vp, right? So this is the conclusion that we can have and use. So now that we know Vp equals Vg, that means Vn is also equals Vg. So basically the voltage that we have here between this point and the negative sign here is basically Vg. So now if you look at the circuit from this side, we have V out here, right? And then if we follow this path, we see that we have Rf, we have Rs in series. Since this one doesn't have any current, it's practically open circuit. So it looks like something like this. We have Rf and then connected to Rs, which is connected to the ground, and this one is also the ground or reference road. So this is Vo, this one is Vg. So now if we know this, This is basically a voltage divider circuit. So the ratio or the value for VG is VO multiplied by RS divided by RS plus RF. So now that we have this, we can write it as this for the value for VO with respect to VG. So we have RS plus RF over RS multiplied by VG. And this one is, it can be simplified as 1 plus RF over RS multiplied by VG. So this is the same conclusion that we had before. So we went through these both techniques to get to the final similar conclusion. So this is an example of a non-inverting amplifier circuit. Again, you should keep in mind that we still have this negative feedback resistor between the output and the inverting input of the op-amp. If we don't have this, then these constraints, the two constraints that we have, they are not going to be satisfied completely. So in this video we went over the non-inverting amplifier circuit, and we looked over two different techniques that can help us to come up with the equation that shows the relationship between the output of the non-inverting amplifier and the input signal.